Hey guys, Unit 6, Thermochemistry, an introduction. There's a second thermochemistry unit later on, it'll be Unit 9, but this one's really introductory, just kind of endothermic, exothermic. We'll deal with Gibbs free energy and things like that later on. When chemical reactions occur, we've talked about this before, physical and chemical changes. Certain things will only happen in the case of chemical changes. Sometimes you get new states of matter, you get fizzing, or you get precipitation that happens, something like that. Maybe there's a color change, maybe it gets hot, maybe it gets cold. There's going to be some additional kind of change that comes from the chemistry that's not just a matter of, melting ice or something like that. Remember, the difference between physical and chemical changes is whether or not we're breaking chemical bonds or not. It's usually how we identify it. And we talked about how, something like an ionic compound dissolving in water, that can be thought of as a chemical change. And I'll show you there's more reasons to think that that's a chemical change, even though it is easily reversible and we don't really form anything totally new. So anyway, a chemical reaction occurs and the temperature changes. That's what we're going to be talking about. Thermodynamics is about heat. It's about the change in temperature of things, right? Heat is going to be the movement of this energy, and we'll get to that. So you can get heat from a reaction. You can have to put heat into a reaction to make it happen. It can happen either way. And if you have to put heat into it, then it's going to feel like it gets cold. And if you get heat out of it, it's going to feel like it's warm, right? What we actually detect when we feel heat is the movement of that energy. When something feels warm, that is heat moving into our hand. When something feels cold, that's taking heat from your hand. You can detect both of those. What you're really detecting, though, is the movement of that energy. The universe is made up of two things. They're matter and energy. Everything can fall into those two categories. And what's especially interesting is that you can turn one of those into the other, which is what happens in things like stars and other nuclear reactions. We're turning matter into energy. But so that's the universe. So far in this class, up to units 1 through 5, what have we done? Maybe it's more having a minute to talk about it. We talked about the periodic table and elements. We talked about bonding and compounds. We talked about intermolecular forces in Unit 3. Unit 4 is where we started looking at reactions. And then Unit 5 was the kinetics, the rate at which reactions happen. And so everything we've really done up to this point has all been about matter, taking reactants, forming products. We haven't really talked much about the energy aspect of it. So take a minute and answer this. Look at the image to the right. Right, so this beaker, got a thermometer. Tell your neighbor what kind of data you can measure or what data you can estimate with regards to the energy in this system. Like, let's say some chemical reaction is going to occur in this beaker with this equipment that we have. What could we determine? Pause the video and think about that. Imagine we do a reaction in this beaker and the temperature goes up. How would that happen? Where's the heat coming from, right? You have to add heat to make that liquid in there expand so that you can measure a different temperature. Where's that heat going to come from? If the temperature goes down, where'd the heat go? Right? How's that happen? These are the kinds of questions you have to be able to answer. So pause the video and answer both of those questions as best you can right now. Where's the heat coming from? Where's the heat going? If I've got an experiment, happens in this beaker and the temperature goes up, where's that heat come from? If I put something in this beaker and the temperature goes down, how's that happen? So I don't know what you remember about bonds, but it takes energy to break bonds. You have to put energy in to break bonds. And energy is then released when you form bonds. We call that energy of formation. So when I look at these two questions that I've just asked you about them going up or down, the temperature going up or down, if the temperature goes up, that means that the energy that I put into the reactants to break the bonds is less than the energy that I got out when I formed new bonds. So I formed new bonds and I got energy out. I put energy in to break the bonds. I must have got more from the formation that came out. That warms up the beaker, makes that thermometer read a higher temperature. And when the temperature goes down, that means I had to put more energy in to break the bonds than what I got back out when I formed the new bonds. And so that took energy from the surroundings and went into that. So it cooled off. First off, thermodynamics, of course, is that energy is not made or destroyed, right? Technically not entirely true under all circumstances because of this whole matter to energy thing. But for chemistry, when you're not talking about nuclear reactions, energy is not made or destroyed. A couple of terms we need to make sure we got straight. The surroundings is everything except for the chemicals in the reaction. So the reactants, the products, that's all the system. The surroundings, if this is happening in this beaker of water and water is not one of the reactants, right? Maybe it's two things dissolved in this beaker of water. The water would be the surroundings. The beaker would be the surroundings. The thermometer is the surroundings. The air outside of the beaker, that's all surroundings, right? So we talk about heat going to those places or from those places, right? It can come from the surroundings into the system, meaning going into the products, or it can come from the system and go into the surroundings, and that's going to read a higher temperature. So the system is always just the chemicals in the reaction, products and reactants. So if the temperature goes down during a chemical reaction in this beaker, that means that heat went from the surroundings into the system. So the products have more energy in them than the reactants had. And that energy came from the surroundings. It came from the water, it came from the thermometer, it came from the beaker, right? And the heat that got taken out of that made that thermometer shrink down, and it lowered the temperature of this whole thing. It'll change the temperature of the water first because that's right there where the reaction is happening. Eventually, that temperature will even out with the surroundings outside of the beaker as well. Occasionally in chemistry, we do work, meaning we physically move something. Remember, work is equal to force times distance. So it means you have to actually move something. Usually what happens is we produce some gas and it changes the volume of something. It pushes a piston to make, some actual work happen. It'll come up occasionally, but it's really rare that you're going to see a problem like that. But it is something to kind of keep in the back of your mind that the energy we're talking about as heat can also be transferred into some kind of mechanical energy to do work. So you may end up, having to account for all of the energy in a system. So a problem may say something like, this reaction happens, increases the temperature by this much, and pushes this piston, which requires this much energy. So you just have to remember that all of the energy added together is going to be whatever came from that chemical reaction. So the temperature change will be some of the energy. The pushing the piston will be the rest of the energy. Those two things added together is the energy you got from the reaction. It's really rare you're going to get a problem like that. But just be aware that work is, it's measured in joules, it's energy. And it's exerting a force over some distance. You're not going to be doing work equals force times distance math, but you might do the heat from the reaction, the energy from the reaction is used to change the temperature and to do some work. And those two things together are going to add up. So it does happen in chemistry in general. AP chemistry doesn't ask much about it, but this is what runs your car. Chemistry, the combustion of the gasoline, is used to push pistons, which is then used to turn your wheels and things like that. So we do work using chemistry. There's also a lot of heat involved in those reactions. And so, you think about the amount of energy that's in the gasoline, that reacts with the oxygen to release a huge amount of energy. Some of the energy is used to push pistons, some is just generated as heat. Those two things added together still should add up to the amount of energy that was in that gasoline, right? Because energy is not made or destroyed, certainly not in chemical reactions. So heat is this transferable energy. It causes a temperature change, but it's energy that moves from one place to another in the form of kinetic energy of particles. So it's this movable energy, when energy moves from one place to another. So a couple of terms we need to know, exothermic and endothermic. If I've got an exothermic reaction happening in this beaker, what does that mean? If it's an exothermic reaction, think of it in terms of energy in the reactants and the products, which had more, the energy to break and make bonds. And I want you to think about it in terms of system and surroundings. So answer each of those three things. Think about the energy in the reactants, the products, the energy in the breaking and formation of bonds, and then how the energy moves, system, surrounding systems, whatever. So pause the video, answer those questions. Okay, so if this is an exothermic reaction, that means that heat is coming out, right? It's endothermic and exothermic. So endo, heat going in, exo, heat coming out. And that's of the system, right? So we've got an exothermic reaction. Heat is moving from the system to the surroundings. It's coming from this chemistry, the chemical reaction that's happening here, and it's going into the water, into the beaker, into the thermometer, things like that. So that's an exothermic reaction. Heat is moving out of the system into the surroundings. And that means that we got more energy out when we form the new bonds than what we put in to break the old bonds. So the reactants, we broke the bonds in the reactants to reform into new compounds in the products. And the energy of that formation released more energy than we spent breaking the bonds, right? So that means that it warms everything up because the heat is coming out. And that means that there was more energy in the reactants than there was in the products. The products are at a lower energy. There was less energy in those because some energy came out. And again, we're not making or destroying energy. So hopefully you can answer all three of those. This is the kind of question AP likes to ask a lot, the kind of conceptual, how is the heat moving? What does that mean for the system, the surroundings? And what does that mean about the bonds? And of course, if this was an endothermic reaction, it would be the opposite of all those things, right? We would be moving from the surroundings to the system. We would have more energy in the products than in the reactants because we had to put energy in from the surroundings. And it would take more energy to break the bonds than what we get out from forming the new bonds. So we talked about intermolecular forces in the third unit. I don't know if you remember that very well, but we talked about ion-dipole interactions. So we want to think about bonds like in an ionic compound, an ionic bond. We want to think about intermolecular associations like those ion-dipole interactions. If I'm going to take sodium hydroxide, NaOH, which is going to dissociate into sodium ions and hydroxide ions, which you hopefully can at least recognize as familiar, even if you don't remember it exactly. So these are going to dissociate. These little purple guys are supposed to be the sodium, and the little red and white, that's your hydroxide. So we're going to throw that into water. It'll dissolve. Now think about everything that has to happen, right? We're going to be breaking some ionic bonds. We're going to be forming new bonds. We're going to be forming new interactions. Add up everything that's going to happen when we dissolve this sodium hydroxide into water. I want every single bond or association that's going to be broken or formed. So pause the video and see if you can identify all of the things that are broken and all of the things that are formed. We're going to break the ionic bond in the sodium hydroxide to get that Na plus OH minus. So we broke the ionic bond, and then we're going to form a ion dipole interaction. We're actually going to form two of these, right? We're going to do the sodium with the water, and we're going to do the hydroxide with the water. And that may be all you got, but there is one more thing that actually happened. For this water to be available to form this ion dipole interaction, we actually had to break a bunch of dipole-dipole interactions. So these are all the things that we had to break or form. Now, if we know this is an exothermic process, then we know that to break these took less energy than what we got out from forming these, because energy comes out. If energy comes out, that comes out when we form bonds or interactions. It doesn't matter if it's a bond or an intermolecular interaction, it works the same way. To form them, you get energy out. To break them, you have to put energy in. So in this case, these two things together required less energy than what we got out from the formation of this. So this is a pretty happy situation. This is a pretty low energy situation when the sodium hydroxide is dissolved in water, compared to having the crystals and having the water on its own. Okay, so knowing that it's exothermic tells us all of that. You want to make sure you think about all of these little steps and how the energy is involved. And if you wanted to list these two separate things as two separate things, that would be appropriate, right? We form an ion dipole interaction between sodium and water, and we form an ion dipole interaction between hydroxide and water. And those are two separate things. So here's your first practice problem. It's a lot like the one we just did. You want to identify all the bonds and intermolecular associations that have to be broken and formed to dissolve ammonium nitrate in water. So ammonium nitrate is going to make ammonium, this guy, plus, and that'll be aqueous, plus nitrate, NO3, this guy. And these are two you should be familiar with in solution. So pretty similar. You should be able to find two breaks and two formations like we did before, but then you need to talk about this endothermic thing. Why is this endothermic? And what does that mean in terms of system and surroundings, in terms of energy of reactants and products, and in terms of energy required to break bonds and released from the formation of bonds? All of that should be addressed in your answer. So take a minute and do that, and then I'll go through it. So when we're looking at this problem, we're going to see that we've got this solid we're going to break. So we're going to break the ionic bonds, right? We're going to break, again, the dipole, which actually, right, is hydrogen bonds. I didn't say that on the last one, but I should have. Remember, AP really likes, if it's hydrogen bonds, don't just say dipole, say hydrogen bonds. So in this case, we are breaking hydrogen bonds. And again, like I said, I should have said that on this problem here. I should make that say hydrogen bonds in big letters because they want to hear you say hydrogen bonds when it's that kind of dipole. So I'm actually going to strike this here and put hydrogen bonds in the water. And then we're going to form ion dipole between the ammonium and the water. And we're going to form ion dipole between the nitrate and the water. So what we know, since this is endothermic, we know that there's more energy in the products than there is in the reactants. We had to move energy from the surroundings into the system, right? Because this is the system now. The water, the ammonium, and the nitrate are all part of the system. And we moved energy into that. And we know that we had to put in more energy to break these bonds and interactions than we got out when we formed these bonds and interactions. So hopefully all of that was in your answer, right? Because that's the level you have to know this. We've looked a little bit at these energy diagrams before when we were doing kinetics. We talked about changing the activation energy with a catalyst, right? We would have a catalyzed reaction that would lower that activation energy and make that more likely to occur. We can look at this in terms of endothermic and exothermic as well. Tell your neighbor, or, at least think it in your head, these reactions, endothermic, exothermic, which one is it? More energy in the reactants, more energy in the products. What would it feel like if this was happening in a beaker? All of these things. So hopefully you can see that both of these are exothermic reactions. Both of them have less energy in the products than they do in the reactants. So that means energy had to be released. One of them has a higher activation energy than the other, but they both release energy, right? We went from this much energy to this much energy in the system, which means that this much energy here was released into the surroundings. This much energy was released by this one into the surroundings. So this one's going to feel quite a bit warmer than this one when they occur in a beaker. And this one, the one on the right, you would also have to add more energy just to get it started. So you've got to practice problems with this too. Identify each of these graphs as exothermic and endothermic. How do you know which one? So do A, B, C, D, just list them on the side, and exothermic, endothermic, and how you know. Wouldn't be a bad idea to talk about system and surroundings. Wouldn't be a bad idea to talk about bonds breaking, bonds forming. Right? Sort all that out. Make sure all that's clear. It's all going to be good practice for you. It matters whether or not this makes sense to you in a way that's lasting and useful. We're done worried about grades. We're worrying about learning now. What you can do is all that matters. Who cares about the grades? That'll come if you can do it. And if it's not a representation of what you can do, then it's not useful. So make sure that your grades are only a reflection of what you can actually do. Also, I want you to figure out which one of these graphs has the highest activation energy, discuss how you know, maybe write a little note how you know. And when you go to answer this question, make sure you realize that the axes are labeled and not scaled the same. And you want to do which one represents the reaction that is most likely to occur at room temperature, and how would you know that? Okay, so all three of those questions you should be able to answer. Pause the video, answer them on your practice packet, and I will go through them here in a second. Okay, so looking at these graphs real quickly, it looks like this is endo. I'm going to go exo, I'm going to go in exo again, and endo again. So that's which is which one has the highest activation energy. So all that matters is how high this peak is based on where the reactants are. So if we look at this one, the reactants look like they're at about 5, and the activation energy, so this is like a 65 activation energy. This is a 140, 200, so this is like a 60 activation energy. This is 140 and 230, so that's like 90 activation energy. And then this last one is 10 and 140, and so that makes it 130 activation energy. So D's got the highest activation energy, and you do have to look at the numbers here because this graph, these two graphs are basically the same graph, right? Just with different numbers on the y-axis. So which represents the reaction is most likely to occur at room temperature? Let me look back at these numbers. This is the one that has the lowest activation energy, so that's the one that's most likely to occur at room temperature. But the lower the activation energy, the lower the energy of the surroundings has to be to make the reaction happen. So at room temperature, if only one of these reacts at one temperature, it has to be the one with the lowest activation energy. And that was B, right, when we did the math. Okay, guys, short and sweet. Like I said, really introductory, just a basic intro to thermodynamics. This whole unit is not much harder than that, so it shouldn't be too bad. Hang in there, you're doing great. First law of thermodynamics.